Welcome to System Design Fundamentals. Today we're diving into one of the most important building blocks of modern distributed systems, the key value store. This is the foundation behind systems like Amazon DynamoDB, Redis, and Cassandra. This is a short summary. First, what problem are we solving? Imagine you need to store billions of key value pairs. Keys are strings like user123, and values can be any data. Think of it like a giant hash table in the cloud. You need to support two operations: put key value to store data and get key to retrieve it. Sounds simple, right? But when you're dealing with terabytes of data and millions of requests per second, things get complex. That's the challenge we're solving. Let's define our requirements clearly. Functional requirements. First, put. Store a key value pair. Second, get. Retrieve value for a given key. The key size can be up to 256 bytes, and values up to 10 megabytes. Non-functional requirements. We need high availability. The system must be available even when servers fail. Low latency. Both put and get should complete in milliseconds. Scalability. We should handle billions of keys and petabytes of data. And finally, durability. Once data is written, it shouldn't be lost. These requirements will drive our design decisions. The simplest approach? Use a single server with a hash table. Put operation. Hash the key, store in memory. Done! Get operation. Hash the key, retrieve from memory. Simple. This works great for small scale. It's fast, it's simple. But what happens when data doesn't fit in one server? Or when that server crashes? We lose everything. No availability, no scalability. This is where distributed systems come in. Let's evolve our design. To scale, we need multiple servers. But which server stores which key? Enter consistent hashing. Imagine a ring from 0 to 360 degrees. We place servers at random positions on this ring. When a put request comes in, we hash the key. Let's say it hashes to 45 degrees. We move clockwise on the ring until we find the first server. That's our primary node. For example, if servers are at 30, 120, and 200 degrees, a key hashing to 45 goes to the server at 120 degrees. Now here's the clever part: data replication. We don't store data on just one server. We replicate it to the next n servers clockwise. If n equals 3, we store the data on 3 consecutive servers. This ensures availability even if servers fail. But who coordinates all this? The coordinator. When a client sends a put request, any server can act as coordinator. The coordinator, first, uses consistent hashing to find the primary node. Second, sends the data to the primary and replica nodes. Third, waits for acknowledgements. Finally, but we're not done. This design has limitations. Limitation 1. Data inconsistency. What if replicas have different versions of the same key? Which one is correct? Solution: vector clocks. Each write includes a version vector tracking which servers have seen which updates. The system can detect conflicts and resolve them. Limitation 2. Handling failures. What if a server goes down during a write? Solution: hinted handoff. If a replica is unavailable, we temporarily store the data on another server, with a hint about where it should eventually go. Once the original server recovers, we transfer the data back. Limitation 3. Permanent failures. What if a server is permanently lost? Solution: Merkle trees. Each server maintains a hash tree of its data. By comparing trees, servers can quickly identify and synchronize missing data. These techniques ensure our system remains consistent, available, and partition-tolerant, even under failures. And that's it! You now understand how to design a production-grade key-value store. We covered consistent hashing, replication, coordination, and failure handling. This is the